Assalamualaikum warahmatullahi wabarakatuh. Welcome back to my video. So in this particular chapter, we will continue with topic number 7 on the transmission line models. Okay, this is the module outline. So we look at the introduction of this topic, followed by types of power lines, and then the brief discussion of short line, transmission line, medium line, as well as long line. So next is the learning outcomes. So after completing this topic, so students should be able to first explain basic structure and components of a tower, as well as parameters of transmission line. So we look at basically at the tower structure and the components that made up this tower, and also the parameters in terms of resistance, capacitance, the series or the shunt connection of the transmission line. So next, so you must be able to categorize the transmission line according to its distance. So we do have particularly three types of distance or three types of transmission line due to its distance, whether it is a short line, medium line, or the long line. So each particular line or distance may have their respective equivalent circuit as well as model for further analysis. And for that, we are going to have the third outcomes on the calculation and analysis in terms of electrical quantities. For example, voltage, current, power, regulation, and also efficiency of the sending or receiving end part of transmission line. So next is the overall transmission system or the generation system of how the electricity is transmitted. Okay, we have first the generation side. Let me change to a better color, purple perhaps. So we have the generation system or the generation sides. So we have the power plant. Okay. We have the power transformer attached to this system for increasing voltage for the transmission or to the transmission. Basically, we have the step up power transformer to step up the voltage rating in order to avoid any losses throughout the transmission system. Okay, so this is one of the reasons why we must step up the level of generated voltage. Okay, so we will go through a long transmission line carrying the HV, high voltage, HT, high tension, and will in between meet transmission substation. So we reduce the voltage or we step down the voltage and before we come to the distribution system. Okay. So from this distribution system or distribution substation where we reduce the voltage, we supply, we distribute again the electricity to the industrial customer. So we do have the residential customer as well as commercial customer. So to look in further details, so this is the source from Congressional Research Service based on graphic found at this link. Okay, page number 5 PDF format. So this is where I picked this diagram from. So this is divided into one 2 and 3, 4 parts. Okay, so the first part is the generation. So generating station. So we have again the generator or the stand-up HV transformer, transmission line with its specification of the rating voltage 765. It may carry 500, 345, 230 as well as 138. It depends on the how far or how long the distance is. So transmission customer in between, somehow we do have the customer where we submit or we transmit the voltage about 138 or 230 kV. Okay. Before we continue to part number 3, which is a distribution part, again we have a substation, step down HV transformer before the demands comes from customer. This is a sub transmission customer, so we have the industrial customer with the rating as well as the commercial or residential customer. Okay. And then having said that, so in general, transmission lines connect the system generators to the system distribution substation. So this is how we can define in general the meaning of transmission line. So it is connecting the system generator where the electricity is generated to the system distribution substation where the demand is coming from. So transmission lines are also used to interconnect neighboring power system. It may also intergrid or interconnected to the grid line where we have multiple source of the generation supply. Okay, so between these generation supplies or generation zone or sites, so it may interconnected to the grid line, the common grid line, where we do have these transmission lines placed. Okay, so since transmission line power losses are proportional to the square of the load current, where P loss equal to I square R, so this is one of the reason again why we do have a high voltage are used to minimize the power losses. So this is the reason why we are supplying or the transmission line is carrying a high voltage to avoid, for instance, the P losses. Right. And then this is a typical transmission line structure. So just to get a general idea on the name of the components which made up typical transformer. We start with, on top here is the earth wire. Okay, so basically they put it on top of the tower. Okay, and then the cross arm here, this is the cross arm. So this cross arm is usually to hold a insulator over here. Okay, the one or the plate, the source, it looks like a plate or it's like a glass source, glass plate. Okay, here, insulated. All right. So we do have the damper. Damper is connected between conductor. All right, so the incoming conductor to the outgoing conductor. Let's say this is the outgoing out. This is the incoming conductor I. So damper is located in between. As well as this phase between phase 1 and phase 2, for example, so we have the spacer in between, okay? In between the conductor. Of course, the cable you see is the conductor, okay, as well as the main body of the tower. Okay. So this looks like a 3-dimension figure of a transmission line. So we can also look at different dimension, which is a 2-dimension figure. And again, just to have a better understanding how the components or the name of the components. So we have the cross arm here, okay, both sides. So we have in between the beam. So on top or tower top, we have the overhead ground wire, the earth wire. Okay, the insulator string over here, this one. Okay, we do have this one as well as this insulator string. And then the conductor bundle over here. So the bundle is the method on how the conductor is being arranged. Alright, so this is the conductor bundle. Okay, again bundle is for the method of conductor arrangement. So the fork over here keep or the name it as keep frame, sorry, tower window. So the width of the tower body, and then the diagonal over here. So the diagonal. So we do have the horizontal member. Okay, so this is all the specific name given to the structure of tower. So the main leg, as well as the tower base, and also the underground pole to strengthen the structure of the tower. Okay, so all in all, we do have the first part, okay, namely tower top. Second part again, tower body, and the third part is tower base. Overhead line components, so conductors, all right, so the main cable carry electric power from sending end station to receiving end station. So we do have three keywords: conductors. So we do have the sending station or sending end station, so to the receiving end station. And then we have another component and the support poles or tower and keep the conductor at suitable level above the ground. And then insulator, so the third component, so attach the support and insulate the conductor from the ground. All right. So since it's carrying the current at high level amount of current, so it must be insulated from the body of the tower as well as the from being grounded. And then the cross arm provides support to the insulators, and then the miscellaneous items such as lighting arresters. So this is all the equipment or the accessories you can find in the miscellaneous item, anti-climbing wires, etc., etc. So this chapter deals with the transmission line model design and its performance under steady state condition. Right. So the equivalent transmission line model is on a per phase basis. So this is per phase basis or all in phase analysis. For example, we have phase voltage or per phase voltage, which is V line to neutral, as well as IP or I phase. Okay. So all equivalent transmission line model again is based on per phase. So two-port networks theory. So this is the term they use to express the voltage and current relations. Again, two-port we will see in detail how they represent or they use to express the voltage and current relationship in terms of two-port networks theory. And then three types of transmission lines, short, medium, longs, are considered as well as the regulation and losses. Okay, so the voltage regulation as well as the losses. So transmission line performances. So transmission line performance is governed by its four parameters. So we have series resistance. So we have series inductance. We have R. Let's say we have the symbol of the series resistance electrically. So we have the series inductance, so Henry, okay. The unit, the dimension is Henry, so we have R, ohms, and then the shunt here, this is a shunt capacitance as well as shunt conductance. Okay, so the leakage current over the surface of the insulator is modeled as shunt conductance. So this is what we can understand by the meaning of shunt conductance. It happens due to leakage current over the surface. However, so shunt conductance is being ignored. Okay, normally we just ignore the value or the element of shunt conductance because the leakage current are too small. So basically there is no shunt conductance, and somehow later on in short line model, so we will see that shunt capacitance is also being neglected. So this is particularly for short distance. Okay, short L or short distance. The equivalent model is again on a per phase basis. Okay, two port networks, and then regulation and losses is being considered or taken into consideration for all type of line. So power type of power lines or type of transmission line. So we have first the short line, which is shorter or equal to 80 kilometers long. Okay, so this is the first category of transmission line. So less than for short line, less than or equal to 80 kilometers. So how about medium line? So it between 80 to 250 kilometers. And longer than that, longer than 250 kilometers, it is considered as long line. So we go for the first transmission line of first model, which is a short line. The definition again, so shorter than or equal to 80 kilometer, or in terms of voltage rating, it is lower than or equal to 69 kilovolts. So what should we do with the impedance? So multiplying series impedance per unit length by the line length. So this is the symbol of the line length in kilometer, of course. So this is the series impedance of the transmission line consisting R and L, right? Resistance as well as the inductance. So Z equal to R plus J omega L. L, so L again, this is the length, okay, in kilometer. Just multiply with R, the resistance value of the transmission line, and also the inductance, okay, of the transmission line. So don't forget the J omega L, so omega here is 2 pi f. So normally frequency is 50 Hz. And Z impedance equal to R plus J X after we multiply by kilometer. So this is the equivalent circuit of short line transmission line. So we have Vs, the sending voltage. On the other part, we have Vr, the receiving end voltage, as well as the apparent power, okay, at the load. So basically, we have the load over here, or receiving part on your right hand side of the diagram. So this is supplying okay, Lying. So this is the supplying and part. Okay, so in between we have Is sending current as well as receiving current, and also the impedance of the transmission line. Okay, So consisting R and also XL over here. Okay. The conductance impedance. And yes, this is another diagram of the short line equivalent circuit. So definition, so for short line transmission, capacitance is always being ignored. So we have, let's say, bigger diagram over here. So suppose we have the, here, let's say we have the shunt capacitance. But in this particular case, or in a short line model, so these have been neglected. Okay, so just cancel the capacitance effect as stated in this notes. So the capacitance effect is always being not. So multiplying series impedance. So per unit length R plus JL by the line length. So this is the definition of R per phase resistance per unit length, L the per phase inductance per unit length, as well as L the line length, and omega is 2 pi F. Short line model on the per phase basis again. So we do have the sending end part over here, and then the receiving end part. Okay. And then Vs and Is are the phase voltage and current at the sending end of the line. So this one, the supplying or the sending part. Okay, so we have again the VR and IR, the phase voltage and current at the receiving end of the line. So we have IR, the receiving current, as well as the VR, the receiving end voltage. So this is how we can understand the equivalent circuit of the short line or short transmission line. Again, consider a three-phase load with apparent power. So this is at the receiving end part. Okay, so this is the elevation of apparent power. SR three-phase is connected at the end of the transmission line. So the receiving end current is obtained by IR equal to S conjugate R, or SR conjugate three-phase over 3 VR. Okay. So this is, again, this is I phase. Okay. All analyzed in phase. So we have over here V phase, or commonly known as VL, VLN. Okay. Single phase or per phase basis. So from there, the sending end voltage is Vs plus VR Vs equal to VR plus ZIR. So if we go back to our previous slide, so we can see over here the closed loop circuit of short line, okay, of equivalent circuit. So from here we can come up with equation that Vs, okay, if we try to apply KVL, so this is equal to VR, okay, so this is this VR plus IR Z. Okay, the voltage drop at this impedance. Okay, so we have IR, or we can say IS, but in this particular example we try to reflect VS in terms of receiving end. So we pick IR multiplied by Z equal to R G plus R plus G GX. Okay, so we have VS equal to VR plus IRZ, or VS equal to VR plus Z IR. It's the same thing. Okay. So this is the first equation. So next, since the shunt capacitance is neglected, so this is what I have drawn over here. So this is the shunt capacitance has been neglected. So what happened? So we can say, or we can have IS is equal to IR. So there is no any branch over here. So 0 branch means IS equal to IR. Okay. And then from there, okay, so we have the second equation. Again, I repeat, IS equal to I, so IR. And these two equations, oops, oh, this is a additional notes over here, means conjugate, so say S equals to 2 plus J3, so thus S conjugate becomes 2 minus J3. So this is just for your additional notes. Okay, and then the two from here we may convert, from to this equation, okay, so we may convert into this model, two-port network or all A, B, C, D representation. Okay, so A, B, C, D representation. So we have the supply or the sending part as well as the receiving part, okay, with I and V respectively. In between the port here is consisting of A, B, C, D element, and we can write this, or we can transform this into, okay, all this into here. Okay, so we try to transform the first equation into A, B, C, D two-port network. Okay, so we may write Vs equal to A VR plus B VIR, and thus we can make a direct comparison. So Vs equal to A, so we supposed to have A VR plus B IR. Okay, so this means from here, so notably A equal to 1 and B equal to Z. Okay, the one we override over here is B, where we replace B or Z with B. So we can say that B equal to Z and A equal to 1 here. Okay, so this is, let me, okay, here this is 1, this is Z. Okay, again from the second equation, here, all right, so if you compare IS, this is equal to CVR. Okay, this is equal to CVR plus DIR. Okay, so let me write in full. This is IS. So try to compare with this second equation. So we can say that C is equal to 0. So here C equal to 0. Okay, so 0 by multiplied by VR. So we can have 0 over here. And again D. Okay, so sorry, this is I. So D equal to 1. Okay. So we can have the same equation, IS equal to IR, where basically we can represent IS equal to CVR plus DIR, and C is 0 and D equal to 1 here. Okay, this one. So C, obviously this is 0 and D is 1 from the second equation. Okay, so or in matrix form, so we have Vs Is equal to A, B, C, D. Okay, so Vi, IR. Here, okay, so this is after we rearrange, so we can understand that A equal to 1. What about B? B equal to Z. C equal to 0. And D equal to 1. And all this replacing A, B, C, D, so we can have the new element of matrix form where I, Z, 0, 1 is again replacing A, B, C, D, VRI, VIR. Okay. Then it is obvious that for short line, again, A equal to 1, B equal to Z, C equal to 0, and D equal to, again, B equal to 1. So what about voltage regulation is defined as the percent change in voltage at the receiving end in going from no load to full load. Okay, so we can simply understand that percentage of VR, voltage regulation. So this is equal to the receiving voltage no load, so minus receiving voltage full load. Okay, and full load. So basically during no load, so the value of receiving during no load, yes, the receiving voltage is slightly higher than the full load. Okay, so when we connect to a full load, basically the receiving voltage may drop. Okay, of course due to some losses. And yes, and no load, so IR equal to FR equal to 0. Okay, so thus VR equal to VS over here, and this is actually derived from the first equation. So let's go back here, here. Okay, oops, not here but here. Okay, so let me rewrite the equation. So we has VA, VS A VR. Okay, so this is plus Z or B. Okay, so remember during no load, IR equal to equal to 0. So then the VR, so NL means no load. So this is equal to VS over A. Okay. So VR during no load equal to VS over A. And then later on we may replace into this first equation or this VR equation. Okay, so VS over A, or let me write over here, VS over A, the percentage of voltage regulation. This is equal to VS over A minus VR full load, okay, oops, over VR full load. VS means the sending current, sending voltage. And basically A equal to 1. So we can simply write that Vs equal to VR over VR. So this simple equation. Okay. For short line, A equal to 1 and VR and no load equal to Vs. Okay. So, and then voltage regulation is measure of line voltage drop and depends on the power factor. So this is how we can actually measure. So how bad the voltage losses or the voltage drop, and of course dependent on the power factor or cos theta dependent. So voltage regulation is poorer at low lagging power factor loads or the inductive load. Okay, so it becomes poorer at low lagging power factor. Then power voltage regulation become negative with leading power factor load capacity. Okay, so this is the example at the lagging power factor where the voltage regulation become positive, because if you look at this phasor diagram, so the VS, okay, the method of VS is longer compared to VR. So this is VR full load. So we have VR regulation. Remember, this is equal to VS minus VR full load, so over VR full load. Okay, so VS in this case is higher, or you can see the diagram or the phasor diagram. VS is much longer compared to VR. This means VS is higher than VR. So whenever VS is higher and VS is lower, this means we're gonna have a positive voltage regulation. So here, okay. So lagging power factor means yes, IR is lagging behind. So it may compute, or it may result in VR is positive. So what about the leading power factor? When the IR is leading a VS as well as a VR, so we have a shorter VS over here. Okay, so this is shorter VS, yeah, dotted line, just to compare with VR. So this is again phasor diagram for the VS. So we can see that here is VR. So VR is full load, of course, bigger than VS. So when we have VR equation, VS equal to VR full loads, okay, over VR full loads, and this is lower, higher, so may produce negative VR. So this is the sending end power equation. So the apparent power is basically, so S apparent power, so this S molar S, the subscript S stands for sending. So we have three phase, 3 multiplied by VS IS conjugate, all sending value. Okay, so the total lines losses is given by SL line. So this is line, three phase. So we have sending apparent power minus receiving apparent power. So the transmission line efficiency is given by here. So the efficiency of the transmission line, PR receiving over PS the sending. Alright, thank you very much for your attention. So we will continue in next video for short line example 7.1. Thank you for watching. See you again.